Okay, that is what that's what we need to test the engine, and we need to say the performance of engine. We have several performance characteristics, as well as the engine is going to operate at a different air fuel ratios, not at a particular speed. Particular air fuel ratio is going to come in, is will come into act, right? So according to the speed, as the fuel air ratio or air fuel ratio is going to differ, the engine operating parameters are always continuously changing. It is not constant for particular thing. For particular speed, particular pressure is constant, but we are not maintaining that particular speed. We are maintaining variable speeds here. Not It is not depending on the specific seat, uh, one particular speed, but we are going to maintain a different speeds. In that way, what we need to do to have higher speeds, we need to give high power output. To have better output, the fuel air ratio should be somewhat richer. But when we increase the fuel air ratio, to when we go to richer mixtures, then there may be lot of fuel consumption is going to be there. So we need to take that into consider. That means the fuel consumption also we need to take. We need to get more power with the minimum usage of fuel. That is what mileage, right? So we, to the maximum extent possible, we need to create such high power by using very somewhat richer mixtures. Otherwise, the whatever the fuel we have is going to be increased in terms of quantity, which leads to the reduced mileage, right? So that's why we need to check a lot of parameters like this. So these are the important parameters which we are going to discuss in this testing and performance. First of all, we will come across performance parameters, and after that we will know how to test these several parameters. Okay, we are going to have maximum cylinder pressure or mean temperature, indicated mean effective pressure, brake mean effective pressure. All this we are going to have. Depending on those only, all these efficiencies and several related parameters are going to be there. Okay, so depending on this, not only whatever I have shown here are not only the parameters of performance, these are the important parameters of performance. In addition to that, we also have some more efficiencies like A standard efficiency, and all these efficiencies will comes under, will play a major role. And in addition to all these five efficiencies, in addition, we are going to have scavenging efficiency, charge efficiency, combustion efficiency also there. Okay, I will explain it after explaining all these efficiencies. And all these efficiencies are going to depend upon the indicated power. First of all, we should know what is indicated power, what is brake power, and what is mechanical work, like that. So first of all, coming to what is indicated power, first of all, there will be thermal energy. Whenever there is combustion of fuel, okay, some thermal energy is going to release. Okay, so within the combustion space, whatever the energy is converted, whatever the thermal energy, whatever the chemical energy, first of all, nothing but indicated power is nothing but conversion of chemical energy into thermal energy. How much amount of heat is released, and whatever the heat is released, how much forces are going to develop to push the piston. That means how much forces are going to help the piston to push downwards. That is what the indicated power. Nothing but indicated power is based on the conversion of the chemical energy into thermal energy. How much amount of fuel is combusted, and depending upon the combusted fuel per unit quantity of fuel, how much energy is liberated. That is what indicated power. And coming to the brake power, okay, here what is brake power? How much energy is converted from chemical energy into mechanical work. That is what brake power. Whatever the available energy at the crankshaft is there, that is what brake power. Okay, whatever the power available at the crankshaft, that means whatever the power useful to run the crankshaft is there, that is what brake power. So that much difference is there. Here indicated power means whatever the energy developed within the combustion space. Okay, that is what indicated power. And brake power means whatever the power developed, whatever the power useful to rotate the crankshaft, that is what brake power. So you got some idea on indicated power and brake power. Similarly, the indicated thermal efficiency is going to depend upon indicated power, and brake thermal efficiency is going to depend upon brake power. Okay, So that's what that means. Whatever the energy converted from that thermal energy to mechanical energy is there. That is what brake power. Okay. Next, coming to I will discuss one by one. So these are the parameters. So these are the important parameters we have. They are indicated thermal efficiency, which is very much important factor, where it is going to decide if the indicated thermal efficiency is high, then brake thermal efficiency is high. Why? Because whatever the energy developed is there, that means it also going to depend upon number of losses also. Okay, if the of course the indicated thermal efficiency is high, but if we minimize the losses, then the most of the energy is going to convert as a the brake thermal efficiency, brake power or brake thermal efficiency. Otherwise, it is going to create losses. Then the brake thermal efficiency is going to reduce. Why? Because here, because of losses, even the indicated thermal efficiency is high. Because of losses, the brake thermal efficiency is going to reduce. Okay, so we need to minimize the losses. But if there is no indicated power, the brake that means the if we have minimum indicated power, the indicated thermal efficiency is less, as well as the brake power is going to be less. That means that is going to create a lot of impact on other efficiencies also. And these two also going to depend upon volumetric efficiency. We already discussed about volumetric efficiency, right? We will discuss again here, and how the volumetric efficiency is going to be calculated also we will know here. And these are several parameters. First of all, indicated thermal efficiency, brake thermal efficiency, and these are the notations which we denote with. And mechanical efficiency is this, nothing but brake power by indicated power is nothing but the mechanical efficiency. Next, volumetric efficiency, we already know this parameter, and once again I will say that to you. Next, relative efficiency, mean effective pressure. This is the main thing which we should know. Why? Because depending upon the mean effective pressure only, all the other parameters, whatever the indicated thermal efficiency are there, indicated power is there, brake power is there, that is going to depend upon the mean effective pressure. Okay, similarly, as like efficiency, as like thermal efficiency, we also have two types of mean effective pressures. One is indicated mean effective pressure, another one is brake mean effective pressure. Okay, so there is a lot of difference between indicated mean effective pressure and the brake mean effective pressure. So we need to know about the both the things. And next, coming to the mean piston speed, nothing but average piston speed. Okay, within the cylinder, whatever the combustion forces are there, those forces are going to push the piston downwards. So there will be varying speeds within the piston. Piston is going to move with varying velocities, right? So the mean piston speed is nothing but the average piston speed, and we have some formulas to derive such piston speeds. I will show you later. Just we will discuss what is mean piston speed. And next, specific power output. Okay, it is going to depend upon the power output by area of the piston. So here the area of piston is also going to create much impact on the performance of engine, right? Whatever the area of piston is there, that should be somewhat minimum. Otherwise the power output is going to less. Why? Because if the power output, if the engine area is high, whatever the power is there, that is going to be consumed by the piston itself. So to here the reciprocating motion, to have a reciprocating motion is one thing, and it also absorbs some energy. Why? Because if it is heavy, it is going to consume some energy. It will become hard for the combustion gases to push it downward. So that's why it is also going to depend upon the specific power output. So as much area as possible, we need to reduce the piston area. Okay, that increases the specific power output. It's just a brief. I will tell you later about a specific power output. Next, coming to specific fuel consumption. Here the fuel consumption is the major important thing to decide the performance of engine. Okay, only the performance of engine is said to be good when it has best specific fuel consumption. That means it should have minimum specific, the fuel consumption should be minimum. Okay, then only it is going to tell the engine as a good performer. Otherwise, if the specific fuel consumption is high, then the mileage is going to be reduced, right? So we can't say that the performance of engine is going to be good. It also, that means the specific fuel consumption also is going to decide the performance of engine here. And as like mean effective pressure and thermal efficiency, we are also having two types of specific fuel consumptions. That is indicated specific fuel consumption (ISFC) and BSFC, nothing but brake specific fuel consumption. Okay, we already know specific fuel consumption at indicated thermal indicated power. That is what indicated specific fuel consumption, and BSFC is nothing but the amount of useful work, or to do a useful work, how much fuel is consumed. Okay, because of fuel, some of the electrical devices are there. Okay, whatever the energy produced, that is not the all energy produced are not going to the brake connecting rod, crankshaft only. Okay, some of the fuel, whatever the fuel consumed and some of the fuel power developed is used to run some of the electrical devices within the automobile, right? So that's why here the indicated specific fuel consumption and brake specific fuel consumption is going to be different here. Okay, and in the same way, inlet valve Mach index. Okay, inlet valve Mach index means it is going to depend upon the area of the inlet valve covered. Okay, and also the area of the uh, cylinder. That means area of the piston. Okay, area of the piston, and depending upon area of that ratio. Okay, area of piston to the area of inlet valve, that is what inlet valve Mach index. We will discuss it later. And next one is fuel air or air fuel ratio. We have come across this air fuel or fuel air ratio so many times. It is going to depend upon the equivalence ratio. Okay, at different engine speeds we need to maintain different fuel air ratios. So we will talk about that later. And next, coming to the calorific value. Okay, so what is calorific value? Nothing but the amount of heat released per unit volume, per unit quantity of fuel. Okay, nothing but the because of chemical reaction, how much chemical energy is converted into thermal energy. That is what calorific value. That means nothing but the amount of energy released by combusting one unit of fuel, like that we can say. That is what calorific value, kilojoule per kg. We will the units are kilojoule per kg, and we will discuss units for every single parameter here. Okay, in next. Okay, next. So these are the things we are going to brief here, briefed here, and now we will go in depth of all these parameters one by one. First, coming to one by one, I will say. Okay, first of all, coming to the indicated thermal efficiency. As I said already, indicated thermal efficiency is nothing but the ratio of energy in the indicated power to the inlet fuel energy in appropriate units. That means both the units should be taken in the same units. Okay, that means sometimes we will take the indicated power in terms of kilowatts, like that. Okay, but the fuel, whatever the energy liberated within the fuel, that is going to be in kilojoule per second. So we need to convert, we need to take both the values in the same units. As it is efficiency, both the units should be in the same way. So that is what in appropriate units. Here I already said you, for suppose this is the energy in the fuel, this is the chemical energy within the fuel, and whenever it has burned, okay, whenever it has burned, what happened? This is the indicated power is nothing but the power developed, whatever the conversion of energy from chemical energy to the thermal energy is there, that is what indicated power. So there are several losses like exhaust, coolant, radiation, etc. So so where it was losing, how it was losing all that, by assuming, okay, some temperature is produced, right? So some of the fuel is going to be consumed by these coolant gases, that means exhaust gases, and also the coolant which we have provided surrounding the engine, and also the radiation. Okay, here what is radiation? To heat, to cool the coolant, we are going to use the water cooling jackets. Okay, once the water cooling jackets are going to achieve some temperature, they should be cooled again, right? There will be circulation of this cooling water throughout the engine, or throughout, there is one circuit for this coolant. Okay, whatever the cooling medium is there, there is one circuit. First of all, it is going to be around the water jackets, and within the water jackets it becomes somewhat hot. So what happens if it is going to be hot only, if we have not replaced that hot water with the cool water, what happens? of course the hot water raises its temperature, and again the same problem is going to be there. That means the it can't provide cooling for the engine parts, right? So that's why we need to provide radiation here. So to provide radiation, what we need to do, radiation means nothing but we are providing some that means whatever the hot water is there, by absorbing energy from the cylinder, these hot water are circulated to the radiator, where the radiator cools the hot water and again sends the this cooled water to the engine. That is what the radiator here. Okay, so some of the energy is going to be lost by this radiation process, etc. So several other factors are also there why we are going to have losses, energy losses in case of this indicated power. Okay, and because of indicated power, within this indicated power there will be some frictional losses and pumping losses. I already said lot of frictional losses, pumping losses, rubbing, friction losses, all those. Okay, so we may have those losses, and because of those to run, and also to run several auxiliaries, some of the power is going to be used. And finally we have the brake power, and this brake power is the main power which is an useful work to run the crankshaft. Ultimately it is the only power which is available for us to run the engine. Okay, so that is what so this is the total. If the chemical energy is the, this is the total energy produced, that means this is the total energy there in the fuel, and when it is going to combust, it is going to produce only this much of indicated power, and that is because of several losses, so lot of losses, and indicated power is only around 40% only. Okay, that means the conversion rate is only if it the energy is 100%, we will get or we can convert the amount of energy to indicated power only as 40%, and brake power is somewhat less, around 33%, 32% like that only. So lot of difference, lot of energy is going to be wasted in these two cases, and here because of frictional losses and pumping losses. Okay, and this is the only available energy for the engine to run. Brake power is the only available energy to run the engine. So that's what you keep in mind, and if you keep these three parameters in mind, you can understand all the parameters very easily. Okay, so these are the three parameters, how the energy is going to distribute here. So I have taken this diagram from the textbook itself. So nothing but indicated thermal energy is nothing but indicated, whatever the indicated power is there, that is led by total energy in the fuel, and brake thermal efficiency is nothing but the brake power by total energy in the fuel. Okay, and mechanical efficiency is nothing but this brake power by indicated power, nothing but mechanical efficiency is nothing but whatever the amount of work converted to mechanical work. Okay, here it is going to convert from indicated power to the brake power, that means indicated work to the brake work. So here whatever the energy available at the crankshaft is, that is what brake work or brake power, by whatever the energy available after these losses, that is indicated power, that is what mechanical efficiency. That means amount of work converted into mechanical work is nothing but the mechanical efficiency. Okay, so that's what brake power to indicated power, which is a mechanical efficiency. So we will discuss one by one regarding thermal efficiencies. I already said what is indicated thermal efficiency. It is nothing but the ratio of energy in the indicated power. So this is the indicated power which we have to the input fuel energy. Whatever the fuel we are going to take into the combustion chamber, in that fuel how much energy is available, that is what input fuel energy. Okay, we have to take both the powers or this power and energy in the same unit. Okay, that is what indicated thermal efficiency here. And if we have high indicated thermal efficiency, the brake thermal efficiency is going to be high. Okay, so in that way we can test the engine by with the help of indicated thermal efficiency. If indicated thermal efficiency is good, then the performance of engine is going to be good. Okay, that is one performance parameter. And here energy, how can we calculate energy and fuel? Nothing but mass of fuel. That means how much mass fuel we are going to take per second into its calorific value. For every fuel there is particular calorific value for this. For suppose if we take SI engine, in that what fuel we will take, gasoline or petrol. Okay, for petrol what is the calorific value? It is somewhat higher than the diesel. Okay, why? Because it shouldn't reach its self-ignition temperature that easily, as there are chances of unburned mixture reach its self-ignition temperature and may create knocking. So that's why the petrol, whatever the petrol we have, that its self-ignition temperature should be high. That means the calorific value is going to be high here. For the petrol also, the calorific value is going to be high. And mass of fuel is going to be the same. That means amount of fuel we have taken, or the here not mass of fuel, mass flow rate of fuel. Okay, per second, how much amount of fuel is going to get into the combustion chamber? That is what mass of fuel per second. Okay, in that way we can calculate energy in fuel per second. Okay, that is what indicator thermal efficiency. And next, coming to the brake thermal efficiency. How can we calculate brake thermal efficiency? Similarly, it is nothing but the efficiency, it is depend as a ratio of energy in the brake power. Okay, whatever the energy available at the brake power or at the crankshaft is there, that is what brake power energy to the input fuel energy. Here we are taking the denominators both as same, only the fuel input energy only. Okay, but only if it is indicator thermal efficiency, we need to take indicated power. If it is brake thermal efficiency, we need to take brake power. Okay, here denominator is same in both the cases, don't confuse. Okay, that is what brake thermal efficiency, nothing but brake power by energy in the fuel. Okay, and how can we calculate energy in the fuel? Mass of fuel per second. How much amount of mass of fuel is going to be burned per second, or amount of available energy in the fuel per second into calorific value of the fuel will give us the fuel input energy. Okay, that is what brake thermal efficiency. Next, coming to the mechanical efficiency. As I already said, it is defined as the ratio of brake power to the indicated power. What is brake power? Nothing but whatever the energy available at the crankshaft. Okay, and what is indicated power? Energy available within the combustion chamber. That is what indicated power. Okay, so that is what mechanical efficiency. In simple terms, to understand very easily, brake power is nothing but delivered power to the crankshaft or engine. To the indicated power means here power provided to the piston. Whatever the forces are there within the combustion gases, that is what the indicated power. And the ratio of these two will give us the mechanical efficiency. And we can calculate indicated power as nothing but brake power plus frictional power. So we already seen here what is indicated power, brake power and frictional power. Frictional power is nothing but friction losses due to friction and pumping. So indicate what is indicated power, nothing but brake power and frictional power. So that's what indicated power. So that's why indicated power is here brake power and frictional power. Summation of both brake power and frictional power will give us indicated power. So finally we have brake power plus frictional power. From this equation we can say that frictional, how can we get frictional power? Nothing but we can know indicated power by using several we can test the indicated power by using several parameters, which we are going to discuss in coming classes. And to know brake power also, we have several devices to denote or to determine brake power. So by subtracting these two, we will get the frictional power, and we can also know frictional power by using several parameters. Several devices are there which can detect frictional power. So several cases are there. How can we find all these powers? We will discuss all those in coming classes. For now, just know what is brake power, what is frictional power, and what is indicated power. So what is indicated power? What is the power available within the combustion chamber? That means whatever the power which is helpful to push the piston, that is what indicated power. And brake power is nothing but what is the power is going to be delivered to the engine, that means a gearbox or to the crankshaft. Okay, meanwhile from transfer of energy from crankshaft to the gearbox is also differs. Depending upon that, some of the power is going to be lost. So that case also there. So we need to talk about brake power is nothing but the power available to run the crankshaft. Okay, that is what brake power. Okay, that is what mechanical efficiency. And coming next to volumetric efficiency, we already discussed this several times, but in different dimension we are going to discuss this. Anything will give us the volumetric efficiency. We already know that volumetric efficiency is nothing but the breathing ability of the engine. It is defined as, we have already defined in two different terms. Okay, one is on mass basis, that means nothing but gravimetric, and another is nothing but volumetric analysis. Gravimetric and volumetric analysis we have already, by using this gravimetric and volumetric, we have already defined this when it comes to volumetric efficiency in first chapter itself, right? So once again we have this opportunity to discuss the volumetric efficiency again, so why can't we go again? So it is defined as the volume flow rate of air. This is nothing but a volume flow rate of air or mass flow rate of air into the intake system divided by the rate at which volume is displaced by the system. The same definition here, it is placed in another meaning. That's it. Okay, the definition is same. Okay, previously we have discussed or we have defined this in another way, but we have changed the names. That's it. Okay, the definition is same, just we have changed the names. Okay, so here mass flow rate of fuel by or mass rate of air. Here why he is specifically talking about air means, if it is CI engine, we need to take only on the air. Why? Because in CI engine, air is only going to get into the combustion chamber. So keeping in mind of these two engines, he specifically controlled on air only. Okay, flow, he has taken flow rate of air only. Of course, here air is in much quantity. Okay, whatever the air is there, that is going to play a major role. Why? Because the fuel quantity is less here. Whether it may be SI engine, the quantity of fuel here we are going to take when compared to air. Okay, that is less here. If we take 1 kg of fuel, we are going to take 15 kg of air, right? So it can be negligible. So it is going to depend upon the volume or mass flow rate of air divided by rate at which volume is displaced, displacement volume. And here rho is nothing but the density, and n by 2 is RPM. That means with how much the speed of the engine here. Okay, and n by 2 it is taken for, if it is a 4-stroke engine, we have to take n by 2. Why? Because for 2 revolutions we are going to take 1 power cycle. Okay, but in case of 2-stroke engine, we can take only single n, no n by 2. We can take only n here. Why? Because for every cycle we are going to have 1 power cycle, right? So that's why in 2-stroke engine we can take n, and if it is 4-stroke engine, it is definitely n by 2. And volumetric efficiency we will discuss only for 4-stroke engines only. That's why he directly given as n by 2. Okay, don't confuse that. Mainly we will talk about volumetric efficiency in case of 4-stroke engines only. As in 2-stroke engines, the suction stroke and exhaust stroke is not going to be there. Only compression and expansion is going to be there. So suction has no particular time to decide that, it has no particular time for that. So that's why he has, keeping in mind that he has given only for the 4-stroke engine this formula. Okay, so what is the volumetric efficiency? Nothing but mass flow rate of air by displacement. Here density also create a major impact. I already said volumetric efficiency is going to depend upon density. Okay, if the density of air is high, the volumetric efficiency is going to reduce here. Why? Because here the residual gases are there which are going to come into act. Okay, so if the residual gases are less, there is more space available for the air to get into the combustion chamber, right? So that's why it is also going to create some impact on density of air, is also going to create some impact on volumetric efficiency here. Otherwise, if we have taken the rotational speed or speed of the engine, this is the formula we have. Okay, nothing but we have to take out the speed of the engine aside. Then we can have same. VD means nothing but displacement volume. Okay. Next, coming to relative efficiency or efficiency ratio. Okay, we have thermal efficiency. Relative efficiency is nothing but the ratio of thermal efficiency of an actual cycle to that of ideal cycle. Okay. Here relative efficiency is nothing but we have A standard efficiency. We already discussed A standard efficiency in the previous classes when we have discussed several cycles like A standard cycles, right? So whenever we have A standard efficiency and in actual cycle we have actual thermal efficiency. Okay, when there is a relation, that means the ratio of this actual thermal efficiency to the A standard efficiency is nothing but the relative efficiency or efficiency ratio. Okay, so this will give us the uh, relative efficiency, and depending upon that we can know the performance of engine. If the relative efficiency is good, okay, then we can say that the performance of engine is going to be good. So that's what we need, why we need to know about the relative efficiency. Okay, if the relative efficiency is good, means that means the amount of developed work is there now, that is going to be most useful. Okay, so it is nothing but the ratio of actual to the A standard efficiency. Okay, this will give us, if the relative efficiency is high, then the performance of engine is going to be good. Otherwise, if it is low in comparison, then it is not going to be a good engine in performance. Okay, that's why we need to know about relative efficiency. In addition to these efficiencies, we have A standard efficiency. We already know A standard efficiency, nothing but what is A standard efficiency? It is both the processes are ideal only, but work output by ideal work output by ideal work input. That is what A standard efficiency, right? We already know that. And coming next to scavenging efficiency. Okay, and here what is scavenging efficiency and where it comes? In case of two-stroke engines, there we need a scavenger, right? It should deflect the direction of air fuel mixture to the spark plug or to the fuel injector if it is CA engine. So here the scavenging efficiency should be high. That means as much as possible, this the amount of exhaust gases are going to get into the atmosphere. Okay, that is what scavenging efficiency. That means how much amount of exhaust gases are thrown away, that much is going to show effect on the engine performance. That is what scavenging efficiency. That means it should throw the exhaust gases into the most possible extent. Okay, next, charge efficiency. Okay, what is charge here? Charge means nothing but air fuel mixture. Okay, so here in case of SA engines, we will talk about this or in post-stroke engines, we will talk about this charge, air fuel mixture in SA engines. Okay, the amount of charge here we need to take as much as possible, as much amount of as possible, more amount of air fuel mixture has to be taken in. Okay, so if we have taken more amount of air fuel mixture, then this charge efficiency is going to be higher. Nothing but amount of fuel taken to the actual amount. Okay, actual ideally enta తీసుకోవాలి మనం యాక్చువల్గా ఎంత తీసుకున్నాం, దట్ ద రేషియో బిట్వీన్ దీస్ టూ ఇస్ నథింగ్ బట్ ది charge efficiency. Okay, nothing but amount of fuel drawn during the suction stroke is nothing but the charge efficiency. Next, combustion efficiency. What is combustion efficiency? Amount of energy delivered from thermal power. That means chemical energy to the, that means amount of energy converted from thermal to chemical to thermal. Okay, whatever the energy is converted, that conversion from chemical energy to thermal energy is there. That is nothing but the ratio of thermal energy by chemical energy. Okay, which gives us the combustion efficiency. That means how much combustion is going to take place. That means if there is complete combustion, then the combustion efficiency is going to be 100%. Okay, if there is incomplete combustion, this combustion efficiency is going to reduce here. So that's what the combustion efficiency. Mostly the combustion efficiency should be around 95 to 100%. Otherwise it may become incomplete combustion. So once there is incomplete combustion, the combustion efficiency is going to be below 94 to 90 and below 94%. So that will create incomplete combustion, and by having incomplete combustion, what we have, emissions are going to be there, which will impact the environment. Okay, which will cause several damages to the health of human. Also to the it will cause several damage to the environment. So we need to make the combustion efficiency as high as possible. Okay, so those are several important efficiencies regarding which here are not shown. Okay, next, coming to mean effective pressure. Okay, I already said what is mean effective pressure. Nothing but indicated whatever the average pressure is going to be there in the throughout the cycle. Okay, so we have drawn PV diagram, right? Whenever we have drawn PV diagram, the area of the indicated diagram by length of the indicated diagram, this is another thing. Okay, first of all I will say about mean effective pressure. This is nothing but the average pressure inside the cylinder. So here the piston is going to travel, or the pressure rise is going to be not constant. Okay, it is not going to be constant. The pressure rise is going to behave, sometimes it may be some 6 bar per second, sometimes it may be 7 bar per second, sometimes it may be 10 bar per second. Okay, there will be some highest and lowest points where we are going to have different pressure rises. Okay, so we need to take, that means different pressures are going to be there because of variation in pressure rise. At different pressures we are going to have different pressures. Okay, so because of that there will be some peak pressure, and also within the combustion chamber there will be some minimum pressure, and later on the depending upon the rate of pressure rise, this pressure also going to increase. So we have to average all those pressures, and that is nothing but the mean effective pressure. So it is nothing but the average pressure inside the cylinders of an internal combustion engine based on the calculated or measured power output. It is also going to depend upon the power output. So what is power output here? Nothing but indicated power and the brake power. So we have two types of power outputs. Similarly we are going to have two types of mean effective pressures. Okay, so indicated mean effective pressure and the brake mean effective pressure. So indicated mean effective pressure is going to depend upon indicated power, and brake mean effective pressure is going to depend upon brake power.